Welcome to another Talk to Myself session. I thought for a change it might be nice to do it live. The question on how many forests can be planted on a two-sphere has been answered last time. 3 forests are enough. And now we can ask ourselves what happens if we take a three-dimensional sphere. So let's just go through the smaller dimensions and see what happens. So this is part 1. Let's start with d is equal to -1. We have the empty graph, and the empty graph doesn't need any forest to be covered. So the arboricity of G is equal to 0. Let's just take d is equal to 0. This is a already interesting graph. We have 2 vertices. So why is this a sphere? It's a sphere because every unit sphere is a smaller dimensional sphere. It's an empty graph. And if you take one away, it is contractible. It's the one-point graph. So here, of course, we need only one forest. So this forest has 2 seats only. There is no edge. D is equal to 1. So maybe let's just take an example of a one-dimensional sphere. So in this case, why is this a one-dimensional sphere? Because every unit sphere of a vertex, the unit sphere consists of 2 points which are separated. So it's a zero-dimensional sphere. So that's a sphere, and the arboricity of G, of course, is 2. You cannot cover it with one forest. D is equal to 2. We talked about this a lot. Maybe I just make a picture of a small sphere. So this is a octahedron graph, and this is an example, and we have seen this is actually the smallest example, and we have seen the arboricity is equal to 3. Now what happens in higher dimensions? So d equal to 3. And of course we would like to know what happens for general D. Now if you look at these numbers, then the natural conjecture would be that it is equal to 4. As a reminder, the join so a G plus H, so you take a graph G and you take a graph H, and the join is a new graph, which is the disjoint union, but additionally you just connect every vertex of the first with every vertex of the second, and so that's the join. So that's the join Zykov. And if you are taking the join with a 0 sphere, then you get the suspension. So G plus 0 sphere is the suspension. For example, this is the suspension of C4. Octahedron graph is just S0 plus S0 plus S0. It's not a prime monoid. It is Zykov monoid. So let's look at the case of small spheres. That's the second thing here, small spheres. So I just call SD, which is SD minus 1 plus S0. So that's actually just the sum. That's S0 plus S0 plus S0. Take just D plus 1 copies. So this is a d-dimensional sphere. Why is it a d-sphere? If this is a sphere, and then you take the join with a with S0, then the unit sphere of this vertex, let's call this sphere WSB, is just S. That's a sphere, that's a d-1 sphere. And SW is also S, it's a d-1 sphere. Now if you take a vertex here on the old sphere, what you have is actually S of x. The unit sphere of S of x is just S of in Sx plus S0, and by induction this is a sphere. So what we have just shown is kind of, maybe I just write it as a lemma. So also interesting is what we can use is we can completely understand the f vector. So let's just take the f function of g. So this is equal to 1 plus f0 t plus f1 t squared plus f d t to the d plus 1, where fk is the number of k plus 1 subgraphs. So this is the f function of g, and we can actually, there's a general relation of the f function of g. F function of h gives us the f function of g plus h. I'm teaching single variable calculus, and a single variable calculus appears everywhere, also here. These are functions, these are polynomials, and generating functions for this. So if you take k of k, and then you take the k of L. If you look at that, all of them are connected with each other. That's just k plus L. So I leave this as an exercise to see. This is kind of pretty cool, right? You have this multiplicity property. So now we can actually give an answer to the question, what is the arboricity of this cross polytope? These are actually called cross polytopes also. These are platonic solids in higher dimensions. If you want to draw the S3, the smallest three-dimensional sphere, what you can do is you can just take a cube, and then you cross each of the intersection is not part of it, but you cross each of them. So let's look at the f functions. So the suspension of the S1, so f of S2 is, what we have is, we have 6 vertices, then we have 12 edges, and then we have 8. Octahedron means 8, right? We have 8 triangles. The three-dimensional sphere, that's what we are interested in. We are interested in this. So f of S3, so that's actually just 1 plus 2t to the 4. It's the gauge group of the weak interaction. It's also the unit spheres of the quaternions, unit sphere of the quaternions. So it's a very important space. But here in the discrete we have just graphs. In order to prove this proposition, we have to get the lower bound and we have to get the upper bound. So first of all, in order to get an upper bound, we just have to construct an example. That's not quite true. I just see that's actually not true, right? It's actually plus 2. So that's not quite true here. so what happens? So it's just bound in an interval now. So I can give a bound. So what I can say, it is actually in 2D. D is equal to 2. So let's just see what happens. I don't know. I have to improvise. So what happens is, so what we have is actually explicitly constructed two more trees actually. These are even trees. We don't even need forests, right? So these are 2 trees. We can take the original trees and then we take 2 more and they form then a thing. So what we have is then, so this is the upper bound is just at d is equal to 1 we have 2, so it's 2d. So we have an upper bound now. So we have an upper bound, and now we need a lower bound. So what is the lower bound? How do we get the lower bound? The lower bound we get with the Nash-Williams. So what we know is, right, the arboricity of G is the maximum over all subgraphs, and then we have the number of edges in H over number of vertices of H minus 1, and so this is so this is bigger or equal, then let's just take that. And I call this the Nash-Williams ratio. So this is just, of course, F0 over F1 over F0. This is F1 over F0. And now, because this is bigger or equal, this gives us a lower bound. This gives us a lower bound. So the Nash-Williams ratio, this is a lower bound. That's very interesting. And so we have a lower bound. Let's just compute it in this case. What is it in this case? What is the Nash-Williams ratio? Right? What is this Nash-Williams ratio in this case? So in this case, of course, it is 0. Almost doesn't make sense here. In this case, also we don't have edges, so let's just in this case it is actually 0. And in this case it is 4 divided by 4, so it is equal to 1. In this case it's 12 divided by 6, it's equal to 2. In this case it is, you can see by induction, it is actually 3. So you see that actually for small spheres, for these cross polytopes, by induction, using this formula here, right, we can just get the expression for the next term. So we get that F1 of GD over F0 of GD. So in dimension D, we have just D. So it is, that's the bound. It is between D and 2D. So that's the correct answer. I had it incorrect before. I only slept over this, so I actually, the night before this talks, I usually dream about what I want to say, and so I was actually dreaming wrong. So in this case, so we have that, and so we have a lower bound. That's very interesting, right? You can now kind of think that in general for a d-dimensional sphere, you know, this ratio is growing linearly. Maybe it is going a little bit faster. So for d is equal to 2, it's between 2 and 4, with the 3 theorem says it's 3. So it's smack in the middle here when d is equal to 2. When d is equal to 1, it was between 1 and 2, and it's actually just 2. When d is equal to 3, so what happens when d is equal to 3, in three-dimensional case, it's between 3 and 6. But these are the small, these are the small spheres. Just remind you about the barycentric refinement. So G and G simplistic complex given by the complete subgraphs. And so what you take is then G1. That's the what you take is here. You take G as your set of vertices, and then you take E. E is talk about this. So for example, you take a triangle, and if this is G, and then G1 barycentric refinement, so you take every of the complete subgraphs is now a new point. So the original vertices were points, then the edges are points, and also the triangle is a point. Maybe I'll just make it red. And then you connect to if one is contained in the other. So the edge, of course, is contained in the edges are contained in the triangle. The vertices are contained in the triangle, and then you get the G1. You get from G to G1. It's just this final plane here. So there's a lemma. Maybe let's call VD. Heron Frobenius eigenvector, the largest eigenvalue, which is just d factorial. So kind of you have, in this case, you made out of one triangle 6 triangles. If you have a tetrahedron, you make 24. So the eigenvalue is d factorial. This gives us a lower bound with Nash-Williams. 1 over VD0 is a lower bound. So in the preprint, which I have just posted last week, where we looked at the two spheres. So this ratio is 1. For d is equal to 2, we have 3. So that was kind of very interesting, because with the 3 theorem actually gave us just a sharp thing here, and then for d is equal to 3, that's kind of what is the topic of today. We get 7, because we have this ratio here is actually just, it's a fraction now, it's 13 over 2, and the next thing is 25 over 2. So that gives us a lower bound 7, and this gives us a lower bound 13. Actually, for large spheres, there are examples where the arboricity is 7. Actually, what is it? So yeah, it has to be, this is a lower bound, right, where it actually has to be 7. So there exist spheres with arboricity equal to 7. Maybe I'll wrap it up. 4, 5, 6 was a kind of obtained here, kind of a bound obtained here. Actually, this is in general an arbitrary d. Now, what happens in 6? We don't know. So, what is the question? Is there a 3 sphere where the arboricity is 8? And I don't know that. So I don't have an example with chromatic number 8, and also here, so we don't have that thing. But now the interesting thing is what happens with these numbers here, these fractions here actually explode exponentially. I cannot prove that yet, but these constants, so this is actually, I call this C1, I call this C2, I call this C3, I call this C4. So the CD grow about like 1.7 something to the power D. So you can look at that with the computer. So this is for every dimension. You get the matrix, you look at the maximal eigenvector, the eigenvector to the maximal eigenvalue, and you look at this ratio, this Nash-Williams ratio, kind of first two entries, and this converges. Of course, this converges in every dimension to a number, so these constants exist. And then you can look what happens when this grows, when the matrices become bigger and bigger, and they, data fitting shows us that they are kind of growing exponentially. Okay, that's it for today.